I'm Dr. Julian Hungerford, a senior application scientist here at Micromeridics. Micromeridics is the world's leading supplier of high-performance systems to characterize particles, powders, and porous materials. Today we're going to be looking at our 3-flex analyzer. The 3-flex is capable of performing both physisorption and chemisorption analysis. In this video, we're going to be looking at chemisorption. The 3-flex is capable of performing both static and dynamic chemisorption measurements depending on model. The dynamic chemisorption model contains a TCD for gas analysis and can also interface with all major mass spectrometer brands for further signal processing. The 3-flex offers the most versatility and precision when analyzing and characterizing catalysts. This demo will cover both static and dynamic chemisorption analysis. Next, we will look at setting up a sample for analysis. Whether you are performing static or dynamic chemisorption analysis, the same sample tube will be used. First, take an empty chemisorption sample tube and weigh it, recording the empty tube mass. Next, load the sample into the sample tube using a funnel if necessary. Use a pipe cleaner to ensure that no particles are stuck to the side of the tube. Quartz wool can be added to the bottom of the sample column to ensure that sample is not sucked into the exhaust port. Record the filled sample tube mass. Next, take the sample tube to the instrument and screw in the sample and exhaust ports. Take a thermocouple and attach it to the instrument. The temperature probe on the thermocouple sits on a ledge on the sample tube. Use a clip to secure it in place. Take the chemisorption furnace and plug it into the power outlet on the 3-flex. Attach the air line to the front of the unit as well. Lastly, place the splash shield on the unit. The sample is now ready for analysis. Let's look at setting up the analysis file in the software. Begin by opening the 3-flex software. Ensure that the instrument is set to chemical adsorption mode by selecting Unit 1, Chemical Adsorption, if performing a static chemisorption analysis. If you are instead performing a dynamic chemisorption analysis, select Unit 1, Dynamic Analysis. Next, raise the elevator into place by selecting Unit 1, Show Instrument Schematic, and Unit 1, Enable Manual Control. Then hover over the elevator icon and right-click, Raise. The elevator will rise to its maximum position and the analysis is ready to begin. To begin the analysis, select Unit 1, Sample Analysis. Then load the sample file that has the recorded mass and analysis conditions. Press Start to begin the analysis. Sample preparation conditions, analysis conditions, and report options can all be preloaded into the sample file, saving you time during an analysis. While the instrument is running, let's talk about the different chemisorption analysis types. Beginning with static chemisorption. During a static chemisorption analysis, the sample will first be prepared, usually by reducing the catalyst by flowing hydrogen at high temperature through the sample bed. Following reduction, the sample tube will be evacuated and subject to vacuum. Next, the sample will cool to the analysis temperature and the adsorptive gas will be dosed, collecting quantity adsorbed versus pressure at several adsorption points. Next, the system will be evacuated before repeating the dosing with the adsorptive gas. The system will then be evacuated again before dosing helium into the sample tube to measure the empty volume in the sample tube. Next, we will talk about dynamic chemisorption. There are several different analysis types for dynamic chemisorption, including temperature-programmed reduction, temperature-programmed desorption, temperature-programmed oxidation, temperature-programmed surface reactions. The general procedure to set up an analysis is similar across the different types. First, we will look at a TPD experiment. During a TPD experiment, an inert gas will be passed through the sample as it is heated. The TCD detector will collect data at the exhaust of the column over time. A mass spectrometer may also be used to examine the outlet species. TPD can provide valuable information regarding the degradation of the sample as it is heated. Next, let's look at a pulse chemisorption experiment using carbon monoxide on calcium oxalate. During a pulse chemisorption experiment, the catalyst should first be reduced. This is achieved by passing hydrogen through the sample while heating. Next, the flow will be switched to an inert gas such as helium. The temperature will then be lowered to the analysis temperature. Next, a stream of carbon monoxide in helium will be passed through the loop in the 3-flex. At set intervals, the loop will dose to the instrument a set amount of carbon monoxide in helium. The TCD will measure the exhaust from the sample tube. Dosing from the loop will continue until saturation has been reached. You will then be able to accurately quantify the amount of carbon monoxide that was dosed to determine parameters such as metal dispersion and the number of active sites. Now let's look at the software features of the 3-flex. Methods can be created that allow you to save time during the setup of analyses for similar samples. The 3-flex will come preloaded with a variety of methods for our standard reference materials for both static and dynamic chemisorption analysis. Once an analysis is complete, reporting features can be used to perform data reduction on your samples. Just navigate to the sample file and press Open. There will be a wide variety of reporting options for different methods for determining metal dispersion, chemisorbed quantity, and crystallite size. There is also the option of creating your own advanced reports through the creation of Python scripts. That is just a quick demonstration on how the 3-flex can be used to collect chemisorption measurements in your lab. If you have any additional questions or would like to speak to someone about your particular application, fill out the form linked below or reach out to your sales representative.